Alright, hello and welcome to the first video in the electrical theory series. This is also the first video for STEM on your own. STEM standing for STEM, Science, Technology, Engineering, and Mathematics. So the whole channel is going to be called SOYO. So let me explain kind of what the intention is. The intention is just to learn. Anybody that wants to learn can. If you're in a different field, or for college students that would like some clarification of things that went on in class, or high school students, just pretty much anybody that has a basic understanding of algebra and such. I'll be going through some of the math as well. So this is more designed for people that learn like me, where being able to pause and process the information that was given is extraordinarily important. But should also be useful for everyone else as well. If you have any questions, feel free to leave them in the comments, or you can send an email. I'll get an email set up here, and I'll leave that in the description below. For reference, the textbook that I'll be referring to throughout this particular series is Electric Circuits by Nilsson and Rydell, 10th edition. I'll leave an Amazon link or something like that in the description as well. Most of the problems and examples that I'll be going through will be coming directly out of the book, but I'll be creating some of my own as well. Now, without further ado, let's get started. So this is session 1, we'll call it. And I apologize for my terrible handwriting. But kind of just getting a general overview on what is kind of electrical and computer engineering. So there's 5 main categories. There's communication systems, there is computer systems, there's control systems, there are power systems, and don't worry, I'll discuss these here in a minute. And last but not least, there is signal processing systems. So as you can kind of see, they're all systems. It just kind of depends on what you're doing. So communication systems pretty much involve anything where you're passing data from place to place. This could be cellular networks to just internet networks as well. FM, AM radio are communication systems as well. Radar, GPS, walkie-talkies, pretty much anything that uses some form of frequency or amplitude to convey information. Computer systems, I think pretty much everybody should be aware of. It pretty much deals with processing information. That can be your cell phone, your calculator, a supercomputer, anything like that. Laptops, desktops. Pretty much anything that processes the information is a computer system. Now, control system is actually probably my favorite, but it uses input from other from sensors and other items, telling the main, what you could consider brain or computer system, and tells that, and that main system will tell something else to move. Sorry. So in an airplane, there might be a altimeter for, let's say, an autopilot. There might be an altimeter, an accelerometer trying to tell how it's tilted, a gyro, anything like that, and that wind, speed, temperature, everything like that, trying to control the plane so that it's not going to crash while the pilots are not fully controlling it. It could even be as simple as a water sensor. If there is if you go to wash your hands and you put your hands in front of the sink, the water will be output. So it switches a relay to allow the water to flow. So we'll just put autopilot as one of the examples. Power systems is another. So this is kind of has to do with the generation and distribution of power. Actually, let's just do a slash here. So that can be power lines, hydroelectric generators, wind generators, anything of that sort. That's really that's what power systems deal with. Now, the power lines are generally actually done by civil engineers as far as designing those, but that will be discussed a bit later in the series. We also have signal processing systems, which they're all kind of interconnected, so you might be able to see that right now. If not, you'll be able to see that as time goes on. But a signal processing system takes one kind of signal. Oops. And converts it to another. Usable signal. Alright, I'm just going to run off to the side here. Doesn't look pretty, but you can have, this could be like image processing, some forms of data compression, or MRI, CAT scans, stuff like that would be all under the idea of signal processing systems. So this is so these are the main ways that or the main areas that we can look at for electrical and computer engineering, which is the whole point of this entire series. So we're going to move on from that, just kind of giving you a general overview. We're going to look now at the differences between the mathematical model and the real circuit. For the vast majority of this series, we'll be looking at just the mathematical model, which is the ideal model, what's termed in physics as the spherical cow. Just everything's perfect, you don't have any weird contours, anything like that in physics. But if we're going into electrical, if you think about it as as you're going into a room and you're trying to flip on a light switch, the light seems to come on instantaneously. That's not actually accurate. There is a time delay given by the length of wire. It does take some time for the electrons to move from the light switch to the wire, or to the light bulb to turn on the light. To our eyes, it seems instantaneous, but it could be a microsecond, picosecond, even a millisecond to actually turn on the light. And with that being the case, it becomes really important. I mean, when you're turning on the light, a human's not going to be bothered by a couple milliseconds of wait or anything like that. But if we're trying to control some high-speed, let's say a control system, or using or you're trying to process information through a computer system, a microsecond or a picosecond could be catastrophic if you don't achieve the right things correctly, or at the correct time. So it's we'll cover this again in the future and more in depth, but to give you guys just a general idea of what this means is the time constant is the delay time, and that is given by e to the negative t over tau, where tau is defined or equal to, if it's a resistor capacitor circuit, it's RC. If it's a resistor inductor circuit, it's L over R. Now T is that time length. So if we have our amplitude axis, which we'll call our A axis, and we have our time axis here, we can have any sort of graph. So an exponential, like what this is here, that will show up more or less similar to this. So let's just say that this right here, this spot, that's our 63% mark. So this would be our e to the negative t over tau time. We'll make this e a bit bigger because that's way too big. So that's the time spot. So that's where, this is where it is 63% of the final value, which is also known as a steady state value. Now, we're going to cover this again in the future, as I previously stated, but I just wanted to give you a brief overview, and just so that you can kind of see things ahead of time. And I guess something that does need to be discussed right now, before we really get too far forward, is that you do need to know SI units. I'm not going to cover those if you don't really understand them. You can just Google it. There's Wikipedia, I'm sure has a site or a page on that. Go ahead and look up SI units and become familiar with those. Kilo, mega, giga, the milli, micro, nano, pico, all those all the powers of 10. You really need to know that. Also, it should be noted that if we have, let's say, times 10 to the, let's say, n, I'm not going to, let's just say k times 10 to the n, I'm not going to actually write out k times 10 to the n every time. If it is one of those powers of 3 that that are in the SI unit base, I will just use that prefix. If it is not in that unit base, what I will do is k and capital E n. That's just the way that I do it. It's a lot easier, I think, and when you have a lot of them in an equation, you don't want to be doing that multiple times. It just confuddles everything. So let's move on to some of the basic definitions and a little bit of the math. So these are just some of the main basic things that we'll need to come across. So lambda here, and this three line equals is, it says is defined as, in case you did not know that, lambda is wavelength. Which is defined in meters, SI unit for length. So, and then we also got C, which is defined as the speed of light, which is equal to 3 times 10 to the 8th meters per second. This is the same C in the equation E equals mc squared. That's the same C, speed of light. So energy equals mass times the speed of light squared. So we can go into frequency, which is defined as F, which is obviously frequency as stated, which is in hertz. And that's the amount of times that it will go through in a second. So if you have a 0 hertz system, that's your DC power. If you have a 1000 hertz signal, that's a kilohertz, and that's it'll go up and down 1,000 times in a second. We've got power, which is defined by P. And this is in watts. Volts, volts is defined by a lowercase v. And we've got current denoted by a lowercase I. This is also called, this is in terms of amperes, which most people call amps, denoted by the capital letter A. Now, I specified V and I needed to be lowercase. That's just a standard that most engineers use, electrical engineers in particular. The only reason why we do that is for DC analysis. If we're doing AC analysis, we use the capital V and the capital I, and that helps us differentiate, especially if we're doing the combination of the two analysis in the same circuit. Now, we're going to go into power and to kind of explain how everything works with that. So, power is equal to volts times amps. So, that's just how it's defined. But it's very similar to the second law of thermodynamics. So, the second law of thermodynamics states that energy cannot be created nor destroyed. This is the same idea for power. Power is conserved, so in all systems. So if things aren't adding up, you're either missing something or you did a calculation wrong. So if you're losing power, it could be through a resistor or something like that, and just being dissipated as heat. So it could be converted. It's the same as if you have a mechanical system. You're not going to keep all the energy in that system. There's going to be some loss to friction, everything like that. But yeah, so let's kind of talk about voltage and current, kind of just to see what they are and how to kind of think about it. Some people try to consider it as water. So there's a cartoon that kind of tries to describe it. So we've got like a pipe here, and it comes down, goes back up. So in this section here, this is resistance, trying to tighten it down. Consider this a lasso. I'm not a very good cartoonist. So current is trying to get through this. And voltage here is trying to kick the current. I'll try to draw a little foot here. But resistance is slowing down the current. That is a way you can look it up online. I don't want to do any copyright infringement or anything like that. Just type in voltage current cartoon and it'll pop up. It should be one of the first 2 or 3. And you'll see what I'm saying the moment that you see it. So it's a funny way of looking at things, and it's technically accurate, but I prefer to think of it in a different way, and I think it might be beneficial to you as well. So if we consider that this plane down here, we'll just kind of color it in a little bit. So we'll consider this the ground, okay? This could be your circuit. I mean, you have grounds in circuits, but in this case, we're just going to consider this just earth ground, what you're standing on, if you're standing. So if we go through, and let's just say that we have a platform at 60 feet, and we have a platform at 100 feet. So we'll say that this right here is 60 feet, and this here is 100 feet. So let's say that we have a bowling ball. So we have a bowling ball in each one. So potential energy in physics is given by mass times gravity times height squared. So assuming that these 2 balls have the same mass, and we'll call that little m, they have 2 different potential energies. So mass times gravity. Gravity is given by 9.81 meters per second squared, or 32.2 feet per second squared. So they have a different potential energy. The one at 100 feet has a higher potential energy than the one at 60 feet. Now, if we go through and convert all that to kinetic energy, which we'll call Ke, this will turn into 1/2 times mv squared. So kinetic energy, the energy is conserved. So by the time that each of these hit the ground, the kinetic energy will equal the potential energy, assuming that there's no air friction or anything like that, which is what we're going to assume, because we're assuming pretty much everything is ideal until later on in the series. So if the mass drops down, which one do you think will be faster when it hits the ground? Well, obviously the one here at 100 feet. So this one has that extra 40 feet here to go faster. And again, this is not assuming this is assuming no terminal velocity or anything like that. So this is going faster when it hits the ground. So this is because these have the same resistance. So we'll just say that both of these have the same resistance R, I guess. No air friction, anything like that. If we were to throw, let's just say, a little parachute onto this one here. I'll try to draw a parachute. I guess here. So let's say we have the parachute there. This, at that point, it might just be, if we get the right size parachute, the 100-foot one might hit the ground at the same speed as the 60-foot bowling ball. It really wouldn't matter. We have to figure that out. But if you have a higher voltage, which is what this height is, so the height is equivalent to the voltage, or comparable to the voltage, then so if you have let's say 60 volts or 100 volts, if you have the same resistance, you have a higher current. And that's related by the voltage equals the current times the resistance. So, that was pretty ugly, I'm sorry. Now, the current is like the speed. So for the same resistance, a higher voltage means a higher current. Let's see. But all right. Well, I think that should be it for this one. We'll discuss resistance a lot more in the next video. If you have any questions, please let me know. Post a comment. I'll try to get to those as quickly as I can. I will post a email that you should email or send an email to if you have a more complicated question than you can do it in comments. Anyways, have a good day, and I'll see you next time.